Okay. And then where is it? Cool. Brilliant.
People trying to get in? No, stop. Okay, well, cheers for coming, guys. I had expected there to be a few more people, but I think with it being a Friday afternoon, maybe not. So I think this would be about 30, 40 minutes.
Yeah, something like that.
Yeah,
half an hour, I guess.
Short Q&A afterwards. So yeah, thank you very much, Dr. Youngman.
Great, thank you. Right, so what I want to talk about today is actually, so some of you might know me actually from second year thermodynamics. And what I want to talk about today is how, from teaching second year thermodynamics, I came to study entropy in single molecule quantum systems. And so I have to admit, when I was an undergraduate, when I was a second year student, and when I was studying thermodynamics, I didn't find it super interesting. So I thought, this is all about steam engines and stuff from like 19th century technology. And, I passed my exam, and then I didn't really think about thermodynamics anymore afterwards. Because the thing that I was really interested in was quantum mechanics, and especially, using quantum systems to do something useful. I was interested in quantum technology and making quantum computers. And one of the things that I was particularly interested in was making a silicon-based nuclear spin quantum computer. So back in 1998, I think, Bruce Kane proposed an idea of making a quantum computer based on the nuclear spin of a single phosphorus atom in silicon. So if you know from sort of semiconductor physics, if you have an impurity atom, such as phosphor, and you put it in silicon, this phosphorus atom has one more electron than the silicon atoms, and it donates this donates this electron to the silicon. Now, if you cool it down to low enough temperature, the electron will be weakly bound to the nucleus of the phosphorus, and because it has a spin, you can manipulate the spin, and you can use it as a quantum computer. So you can store information essentially in the superposition of the spin state of the nucleus of the phosphorus. And this was something that I was super interested in when I started my PhD. And one particular question that I wanted to answer was, how can you manipulate this spin? How can you make a quantum computer out of it? And to understand that, what we really wanted to know was, what does the wave function of an electron bound to a phosphorus atom in silicon, what does that look like? So when I started my PhD, the experiments that I was doing was I was using a scanning tunneling microscope to look at the wave function of electrons bound to a single phosphorus atom in silicon. Now, if you remember from your quantum mechanics course, a scanning tunneling microscope is essentially, it's a very sharp needle. It's an atomically sharp needle that you scan over a surface, and you bring it close enough to the surface that electrons can tunnel from the substrate into the tip. It turns out that electrons tunnel from the substrate to the tip, giving you a current, and it turns out that this current is proportional to the wave function squared of the electrons. So if we have a phosphorus donor in silicon, you have the electron that's bound to that phosphorus donor. You have a wave function. By looking at it with a scanning tunneling microscope, you can image the wave function of the electron bound to the donor. So that's what's shown in this bottom right image here. So the sort of bright yellowish, whitish thing that you see there, that is actually the wave function squared of an electron bound to a single phosphorus donor. So it's a few nanometers in size, and the sort of weird shape that it has reflects the crystal structure of the silicon. And in fact, by looking at the shape of the wave function, you can tell how far away your donor is from the surface. And the reason that we want to know this is because if you build a quantum computer out of phosphorus donors in silicon, the way you make the quantum bits, the qubits, talk to each other, interact with each other, that is via the overlap of the electronic wave function. So as you see, the wave functions look a bit weird. So clearly the interaction of the wave function depends on how you position those atoms with respect to each other. So that's why it was important that we knew what those wave functions look like. Now, of course, a donor beneath a silicon surface with an STM tip above it, that is not a quantum computer. That's not a device, right? So the next thing that we were interested in and that we started looking at was how can we actually make a device out of these things. And around about the same time as we were looking at those donors with a scanning tunneling microscope, we also got very small silicon transistors. So if you look at your phone or your laptop now, the transistors in there, I think they're called the 14 or the 7 nanometer node. So that means that the critical dimensions of these transistors are 14 or 7 nanometers, and they're formed in what's called a FinFET geometry. So this is essentially, so the silicon channel is like a little fin, and the gate, an electrode wraps around it. And the channel through which the current flows is very small, so it's only a few nanometers. And if you calculate with a given donor concentration how many impurity atoms there are in the channel, so how many phosphorus atoms you have in the channel, that's only 1 or 2. So what we did was we took those silicon transistors, which were at that point they were being tested for sort of the next generation computer chips. So we got our hands on a couple of those, and we cooled them down to very low temperature, to sort of bit less than a Kelvin temperature, and we measured an electrical current through them. And what we found was that for some of these devices, you get if you measure the current as a function of the gate voltage, so as a function of the voltage that you apply to this electrode that's wrapped around the channel, you get these little peaks in the current. And those peaks, they correspond to the energy alignment of the energy levels of the electron bound to the donor and the energy of the electrodes. So if you look at the picture on the top right here, you can imagine this is sort of an energy diagram of what the transistor looks like. And what you have is you have a source and a drain, in which you have a continuum of electronic states, and that continuum of states is filled up to a certain energy level, to the electrochemical potential or the Fermi energy. And you have that build up to this energy. And then in between, you have a donor. And this donor, of course, has discrete energy levels because the confinement. You remember from quantum mechanics, your hydrogen atom has discrete energy levels, right? There's the 1s, the px, y, and z. So an electron bound to a donor in silicon has exactly that. So if you apply voltage to the gate, you can shift those energy levels up and down, and only when the energy level of the dopant atom aligns with the Fermi energy of the electrodes can an electron go from one electrode onto the donor and then off again. So this gives you a way to study the electronic properties of a single donor in a device. Now again, there's a bit of a problem here, that if you want to make a quantum computer out of it, it's all well and good that you can find a single donor randomly placed somewhere in a silicon channel. But of course, if you want to make a device out of it, if you want to make a computer out of it, you want to know where all these donors sit with respect to each other. As I just said, the interaction between them depends on the wave function overlap. So they need to be very precisely placed in order for the thing to work. And that's obviously not the case in such a device, because they're sitting there randomly. So while I was doing this research, which I'd initially started in Delft, in the Netherlands, where I'm from, I'd moved to Australia to Center for Quantum Communication and Computation Technologies, which is one of the big groups in the world working on silicon-based quantum computing. And one of the things that they managed to do there, which is very impressive, was they found a way, again using a scanning tunneling microscope, to place donor atoms on the silicon surface with atomic precision. So an STM allows you to image with subatomic precision, so you can really see where all the atoms are. And the method that they developed there was that they took a silicon surface and they passivated it with with hydrogen. So if you take a silicon surface, it typically has one, so that each silicon atom that sits right on the top has one unbound orbital. So it wants to pair up with another silicon, but there's no silicon on top of it, so it sticks out. You can passivate that by putting a hydrogen atom on there. So what you have is you have silicon, and each silicon atom has a hydrogen atom stuck to it. Then you can come in with your STM tip and you zap the hydrogen atom up. You apply a large voltage, the hydrogen atom pops off. So now what you're left with is a silicon surface, still completely covered, passivated with hydrogen, and only a couple of little holes in there where you've removed that single hydrogen atom. And then you can come in with a precursor gas, so with phosphine, which is a phosphorus with a couple of hydrogens around it. And this sticks to the silicon, but only where you've removed the hydrogen atoms. So, and it sticks there. You can then heat it up a little bit. It gets incorporated into the structure. You overgrow it with a couple of layers of silicon, and you have your phosphorus atom sitting right where you want it with atomic precision. And this is an experiment that my colleagues in Sydney did. So this is again measuring the current through a device where they placed a single phosphorus atom. So here on the left here, you see a source and a drain electrode that they've made by removing the hydrogen atoms and then dosing it with phosphine. And then right in the middle, sort of 9 nanometers away from the source and 9 nanometers away from the drain, there's a single phosphorus atom there. And what they do then is they, again, using a gauge voltage, they can move the energy level up and down. And with a bias voltage, they can move the chemical potential of the electrodes up and down. And then you measure the current or the conductance. So that's the current divided by the voltage, essentially, as a function of this gauge voltage and the bias voltage. And what you see is you get these very nice diamond-shaped maps. Yeah.
How many hydrogen atoms we remove from the chip?
Well, for the single.
Is there a specific number or it just
Well, for the electrodes, you remove a lot of them because you don't want any hydrogen there. But for the single donor, you have to. I think you remove a couple actually. I think you need a couple of clean silicon sites to put a single phosphorus in there. So you make a device out of that where if you measure the current as a function of the gate voltage and the bias voltage, you get this nice diamond pattern, which is indicative of single electrons going onto the phosphorus donor and then off again. So the current goes as it's known as sequential electron tunneling. So electrons tunnel sequentially from the source onto the donor and then onto the drain again. And you have these regions where the current is blocked, where there's no current flowing. The reason for that is that, electrons, they repel each other. So if you have one electron sitting on the phosphorus donor and you want to put an extra one on there, you have to pay the charging energy because they repel each other, the Coulomb interaction. And therefore, for some combination of gate voltage and bias voltage, you don't have enough energy to hop across. And this is known as Coulomb blockade because of the Coulomb repulsion of the electrons. So what this here shows you is a single electron tunneling across a device made of a single phosphorus atom in silicon. So this was sort of what people could do in Sydney when I finished my PhD there. Now, I thought this is, and I still think this is amazing that you can place a single donor atom with atomic precision in a silicon substrate. But I'd finished my PhD. I thought it was time for something new, and I left Australia and I moved to the UK. And I thought, rather than trying to place the donor atoms sort of top down, is there a way we can do it bottom up? And the answer is yes. It's exactly what chemists do all the time, right? A chemist, a chemist can synthesize a molecule with atomic precision. A chemist knows exactly where all the atoms in the molecular structure are. And Whereas the previous device that I've shown you, that takes weeks to place a single donor exactly where you want it. A chemist can make 10 to the 23 molecules, 10 to the 26 molecules, I don't know, no problem, right? Just pouring some chemicals together. So molecules are atomically precise structures that you can make at very large scale. So when I moved to the UK, I thought, can we make atomically precise structures, molecules, and study the quantum properties of those things? So what I started doing about 8 years ago, I think, when I came to the UK to start my postdoc, I took a molecule and I placed it between two electrodes. So what we did was we made a pair of electrodes that are about 1 or 2 nanometers apart from each other, so roughly the size of a single molecule. And then we deposited molecules across the substrate, and some of those molecules end up sitting right between those two electrodes, so sticking between those two electrodes. And again, we use the same kind of way of measuring. So we can apply a voltage, a bias voltage across the molecule, so the current starts flowing, and we have a third electrode, a gate electrode, that allows us to move the energy level of the molecule up and down. And whenever the energy levels of the molecule align with the Fermi energy of the electrodes, you get a peak in the conductance, so you get electrons going across. And one of the interesting things that we found with these molecular devices was that, unlike the silicon devices, unlike the sort of semiconductor devices, molecules are very floppy. So if you have a silicon device, all the atoms, they're pretty much there, they're stuck, they don't do very much. For a molecule, all those atoms are sort of wiggling around and shaking and vibrating and doing all sorts of things. And they essentially act like harmonic oscillators. And we know, of course, from quantum mechanics, if you have a harmonic oscillator, you have that has discrete energy levels as well, and they're equally spaced, right? That's the yeah. So what we found for these molecular devices was that if you measure the current, each time you hit a resonance of the harmonic oscillator, there's a little jump in the current. So here on the bottom right, you see the conductance. So again, it's the derivative of the current with voltage, essentially. And what you see is that there's little peaks in that conductance, and those peaks are equally spaced. And that spacing corresponds exactly to the discrete energy levels of a harmonic oscillator. And this harmonic oscillator in this case is so it's not, it's not a ball on a pendulum or a mass on a spring, but it's actually the molecule sort of vibrating, and we think it's sort of a motion like this. If you look at the molecule on the top left here, it has these two sort of anchor groups that stick to the electrodes, and what we think happens is that there's some sort of rocking motion of those anchor groups, and it's that harmonic oscillation that you're driving. So by measuring the current through a single molecule, you can actually study its electronic quantum degrees of freedom, but also its mechanical, so its vibrational quantum degrees of freedom. So it's really a sort of atomic scale harmonic oscillator. Now, up till now, we've sort of been looking at these devices where you operate them essentially as a transistor, right? You have a source and a drain, so you apply a bias voltage across it, and you have a gate voltage, and you look at the current as a function of that. Now, what we also started to do a couple of years ago was to look at these devices and rather than applying a bias voltage across them, we're applying a temperature bias across them. So we had, this is actually data from one of my co-workers in the Netherlands. So we had, I don't know if you can see it very well, but again, we have a sort of junction, two electrodes, roughly a nanometer apart, with a molecule in between. And now on either side of the junction, we have a heater. So we can pass a little current through the heater. It heats up via Joule heating. And if you heat up one side of the junction, but not the other side of the junction, you get a temperature gradient, a temperature difference across your junction. And it turns out that this temperature difference also drives an electrical current. So again, my collaborators, they measured first the current as a function of gate voltage and bias voltage, and that looks again similar to what we've seen before. So you have regions where there's no current, where there's Coulomb blockade, and then you have regions in between where the electrons can tunnel via sequential electron tunneling. If you look at the conductance, that's essentially just the derivative of that current with respect to bias voltage. But then we could also measure the thermal current, so the current as a function of the temperature difference. And that's what's shown in this map on the right here. And this is where I slowly started to think about thermodynamics again, because if you think about thermodynamics, and this was roughly at the time when I moved to Queen Mary and started teaching second year of thermodynamics, and this was roughly in week 4 when I was talking about heat engines, and I thought, you have a hot reservoir and a cold reservoir, and there's something in between. There's an engine in between that generates work, and the work in this case is the electrons that are moving, like it's generating electrical power essentially. So this is starting to look a little bit thermodynamics. Although having not thought about thermodynamics for a long time, I could sort of see that there was a similarity there, but that's kind of where it ended. But then my co-workers also looked at this device as a function of temperature, and they looked at the conductance peak as a function of the gate voltage. So the conductance peak, as I said earlier, you get a spike in the conductance. But that's not entirely true. Actually, there's a little shift, and that shift depends on the temperature. So what you see here is on the left, you see the conductance as a function of the gate voltage, so as a function of the alignment. And then for different temperatures, so starting at 2 Kelvin, going up all the way to 10 Kelvin. And what you see is that that peak is shifting a little bit. And if you plot the shift of that peak as a function of temperature, and you look at the slope, then that slope is equal to the Boltzmann constant times logarithm of 2. And then I thought, okay, that must be something thermodynamics, right? Because KB ln of 2, that's like thermodynamics. So that's when we really started thinking, that there might be something, there might be something here. And round about the same time, two papers came out, one in Nature Physics and one in Nature Comms, about of quantum systems. And one was using a sort of conductance measurement, similar to what we'd been looking at. The other one is slightly different, looking at a charge detection. So actually looking at how many electrons there are on the molecule or in the single electron transistor. And my PhD student, Eugenia, who actually also demonstrated for thermodynamics the first year that I taught it, she thought, both these methods, there must be the same underlying principle to them, and that underlying principle must be simple second-year thermodynamics. So she set out and looked at those two papers. Those two papers gave a very difficult, very complicated explanation of why they were actually measuring the entropy. And Eugenia said, no, it must be simple thermodynamics. So she came up with an idea. So essentially, again, this is the energy diagram of what's happening. So you have an energy level of your molecule. It's coupled to two reservoirs with electrons that obey the Fermi distribution, and depending on the alignment between the molecular energy level and the electrochemical potential of those reservoirs, you get more or less current or conductance. And what we started out with was just writing down the Maxwell relation for such a system, and you know from thermodynamics, you know all these Maxwell relations, and it's all these partial derivatives, right? So we just wrote down the simple Maxwell relation for a molecule sitting next to a reservoir. And then we used the thermodynamic identity, which again is sort of second-year thermodynamics, to relate the energy of the system to essentially the temperature and the change in entropy with respect to the average number of electrons that you have on your molecule. And then we use the Gibbs entropy to work out what that entropy was. And in the end, we ended up with an expression that you see on the bottom left here. And what it essentially tells you is that the shift in energy for which you get your conductance peak, that depends on the difference in entropy between having no electrons on the molecule or having one electron on the molecule. So this delta S, all the way in the bottom right here, that is the difference in entropy between having 0 or 1 electron on the molecule, or between having n and n plus 1 electrons on the molecule. So by measuring the shift in energy, you can actually directly measure the entropy of the electrons on the molecule. And this is exactly what we started out doing. So again, with my collaborators in Delft, we took a molecule. If you're not a chemist, then this molecule doesn't mean anything. It didn't mean anything to me either. But this is it's a free radical, and that means that there's one unpaired electron on there. So normally, if you have a molecule, the electrons like to pair up, right? So every spin-up electron wants to sit next to a spin-down electron. Chemists can make free radicals that have one unpaired electron. They're very reactive. That's why you don't want them. You don't want them inside you because they cause all sort of damage. But they're interesting to study because they have one unpaired electron. So again, what we did was we measured first the conductance as a function of bias voltage and gate voltage. So again, it looks the same, different color scale, but it's the same thing. So you get regions where there's no conductance, where there's Coulomb blockade, and then regions in between where you do get conductance. And we also looked at the thermal current. So that was the current that you get as a result of the temperature difference. And what she did was she wrote down an expression for the conductance and an expression for this thermal current, or the thermoelectric conductance. And if you look at those two equations, what you see is that the first one, for the electrical conductance, it's essentially 1 minus the Fermi distribution times the Fermi distribution shifted by an amount, temperature times the change in entropy. So if the change in entropy is 0, then what this does is it gives you a peak that's centered around epsilon equals 0. If the delta S is non-zero, it will give you a shift of that peak. So that's that is what happens with the conductance. So it's a peak and it's shifted with respect to epsilon equals 0. If you look at the thermoelectric conductance, you get that same expression. So 1 minus F times F, which is shifted by TdS. So again, it's like a shifted peak, shifted from epsilon equals 0, but then it's multiplied with epsilon. And epsilon, so that's a function that's odd and it's centered around epsilon equals 0. So if you have a function that's odd and centered around epsilon equals 0 and a symmetric peak that's shifted with respect to epsilon equals 0, what you get is a sort of an asymmetric shape. And the degree of asymmetry depends on TdS, T delta S. And that's exactly what we measured. So here we measure the thermal conductance on the top as a function of gate voltage, as well as the electrical conductance as a function of gate voltage. And what you see is that if you look at the blue curve here, the conductance peak, so that's the bottom one, that's shifted slightly with respect to epsilon equals 0, and the thermoelectric conductance, you see that there's a slight asymmetry. So you see that the peak goes up to 0.5 or something, and the trough only goes down to 0.4. So there's this asymmetry. And this asymmetry is a direct measure for the entropy of the system. So that was interesting. So that meant that we could measure the entropy of a single molecule. But we wanted to take it a little bit further. And what we did was we applied a magnetic field. And now something really interesting happens. As you apply a magnetic field, you see that the asymmetry starts to change. So at about 6 Tesla, you see that the thing is pretty much symmetric. So the peak is at 0.4 and the trough trough is at minus 0.4, so it's symmetric, or, well, anti-symmetric actually. And then at 8 Tesla, the asymmetry is sort of inverted compared to at 0 Tesla. So what this means is that by applying a magnetic field, we can change the entropy of the system. We can control the entropy of the system. And now to explain this, now we have to think about what happens when you apply a magnetic field, and you have to think about what happens if you with the spins in your system. And as I said earlier, because this is a free radical, you go from an unpaired electron to so in its neutral state you have one unpaired electron, and then if you add one extra electron to there, you have they pair up. So in the n charge state, so the neutral charge state, you have one electron which can be spin up or spin down. So at 0 magnetic field, that corresponds to having 2 microstates. So if you remember from the Boltzmann definition of entropy, right, there was kV ln of omega. So on this, I think on this tombstone it says K log W. Apparently those were the letters that he used for it. So at 0 magnetic field, for an unpaired electron, it can be spin up or spin down, so you have 2 microstates. But then if you add one electron to it, that electron is going to pair up and it's going to form a singlet. So this is essentially a state where you have spin up, spin down, minus or plus, I always do it, plus, spin down, spin up. So this is a way in which the 2 electrons pair up. There are other ways of pairing them. You can also have up, up, or down, down, as well as up, down, minus, down, up. But those have a higher energy, and the reason for that is because they have to sit in different orbitals, right? Because it has to do with the fact that they're fermions. They have to be antisymmetric under exchange. So this is the exchange interaction essentially. So 1 electron, 2 microstates. 2 electrons, only 1 microstate. So if you measure the difference in entropy between those two microstates gives you an entropy of kV log of 2, 1 microstate kV log of 1, which is 0. So as a result, the difference in entropy between those two is minus kV log of 2. And that's exactly what we measure at 0 Tesla. So you get a difference in entropy of minus kV log of 2. Now, if you start applying a magnetic field, what happens is you start splitting the spin states, right? You get Zeeman interaction. So the spin down goes down in energy, spin up goes up in energy as a function of the magnetic field. And the same thing happens with the singlet and the triplet states as well. And if you apply a large enough magnetic field, so if you were to go up to 12 Tesla, then for the neutral charge state, the spin down has gone down in energy so much that is the only state you can be in. So for the neutral charge state, you'll only get 1 microstate. Whereas for the n+1 charge state, there are now 2 microstates accessible. You can have the singlet state, which doesn't change with magnetic field because the spins sort of cancel out. But then one of the triplet states has come down as well. So the down-down triplet state goes down in energy with magnetic field, but both align with the magnetic field. And at some point they meet up, those 2 energy levels. So that happens here at 12 Tesla. You see that the green line corresponding to the singlet state meets one of the blue lines corresponding to the triplet state. And therefore at 12 Tesla, again, you go from having 1 microstate in the neutrally charged molecule to having 2 microstates in the n+1 charge state. So now you have a difference in entropy of logarithm of 2 plus kb logarithm of 2. Now unfortunately our magnet didn't go all the way to 12, but what you can see is you can actually calculate the difference in entropy between 0 and 12 Tesla. So that's on the top. You see the blue line, the solid line. That's the predicted change in entropy. And then the data points, so those come from the measurement from the asymmetry of the response, they fit very nicely with that line. So really what we can do here is by changing the magnetic field, by changing the spin quantum degree of freedom of the molecule, we can change its entropy. We can change the number of microstates that are available and therefore the entropy. So we've written up this paper. It's under review with nano letters. I think it'll be published soon. But now we thought, okay, now we can essentially do everything thermodynamics, right? So the first thing that we now started looking at was can we create a system that has more than 2 microstates? So now the spin gives you 1 degree of freedom, so it can be spin up or spin down, but that's it. So we thought, let's make a bigger molecule, and in this bigger molecule, not only do you have the spin degree of freedom, but you also have an orbital degree of freedom. So the electron can sit on the left side of the molecule or on the right side of the molecule. So now you have more microstates. You have the microstate spin up, spin down, but you also have the microstate left, right. So you actually have 4 ways of arranging your electron. And sure enough, if we found a different way of measuring the entropy for this system. So rather than looking at the asymmetry of the thermoelectric conductance, we looked at the difference in current for positive and negative bias voltage, which is also a measure for the same kind of entropy. And what we found was if you go from 0 electrons to 1 electron, you have a change in entropy of kb log of 4. The reason for that is 0 electrons, there's only one way to arrange that. If you have 1 electron, you can be spin up, spin down, left and right. So that's 4 ways of arranging your electron. So that gives you a change in entropy of kb log of 4. If you put 1 extra electron on there, so if 2 electrons, then again there's 4 ways of arranging it. So then you get a change in entropy of 0, because there's 4 ways of arranging 1 electron. There's 4 ways of arranging 2 electrons. So you get a difference in entropy of 0. And then there's all sorts of other thermodynamic variables that you can extract from the entropy, of course. So now I just take my Finn's thermal physics and I flick through it. Heat capacity. Heat capacity is the derivative of entropy with logarithm of temperature. And we're doing that experiment now. So we're measuring the entropy as a function of temperature, and we can measure the heat capacity of the system. Now, that's of course very interesting. That's fun to do. All of sort of classical thermodynamics onto this quantum systems. But is it also useful? And that's really the last thing that I want to say about it. So why might it be useful? One thing to think about is if you think about thermodynamics and why it was initially developed, like in the 19th century, that was because people wanted to have their engines to be as efficient as possible. And you know the Carnot efficiency, it's 1 minus T2 over T1. For an engine, it's 80%. And the engine of your car, the engine of my crappy Skoda Fabia, is about 50% or so. So it's of course never exactly the Carnot efficiency, but it's pretty close to it. So it's at least sort of the same order of magnitude. Now there's also a thermodynamic limit for computing that's known as the Landauer principle. And what that essentially tells you is that the minimum amount of energy required to erase or create 1 bit of information is given by kBt logarithm of 2. And you can just derive that from thermodynamics. Now kBt logarithm of 2, that is about, at room temperature, that is about 3 zeptajoule. So a zepta is 10 to the minus 21, I think. So that's a very small energy. If you look at a transistor in your laptop or in your phone, to switch on or off a transistor, it takes about 1,000,000 times more energy than that. So whereas your Skoda Fabia is same order of magnitude as the maximum sort of maximum efficiency allowed by thermodynamics, your computer is 1,000,000 times worse. The computer that you have in your head it's a bit better than a computer in your laptop, but it's still orders of magnitude. The energy required to fire one neuron is still orders of magnitude greater than 3 zeptajoule. So, and of course, the energy required to create or erase 1 bit of information is exactly the thing that we've just measured. It's the temperature times the change in entropy from having 0 microstates, from having 1 microstate to having 2 microstates. So what we're now, by being able to measure the entropy of a quantum degree of freedom, we can't do computations with them yet, but at least we know how much energy it takes to create or erase 1 bit of information that is encoded in this quantum degree of freedom. So whether you do classical computation, where you just use spin up as a 1 and spin down as a 0, or you use quantum computation, where you use the superposition of this up and down, the energy that is required to create or erase that bit of information, that is exactly the energy that we've just measured for the single molecule. And with that, I'd be happy to answer any questions if you have them.
Right, instant question, just because you sort of brought it up. From your preliminary research, because everyone obviously looks at quantum computers as this wow, amazing, possibly world-changing thing, are they much less energy efficient or much more energy efficient at the moment?
Right.
Than
So
a conventional chip.
at the moment, the problem is that they only work at very low temperatures, and to cool something down to very low temperature, it takes you a lot of energy to achieve that. So, and that's also not the big selling point, I think, of a quantum computer. It's not the energy consumption per se. It's the fact that you can do certain computations exponentially faster than you could do it with a classical computer. But there is definitely an interest in low energy computing, be it quantum or classical computing, and there's a simple reason for that, right? You want your phone to last a week instead of 8 hours or whatever. So there's definitely a need for low energy computing, and by doing these kind of measurements, you can at least show that this is, if you encode information in something like a spin, that is the lowest amount of energy. That of course, when we do our experiments, it's the same problem, right? I can say, when an electron goes off, it takes kV logarithm of 2 of entropy times the temperature. Of course, the actual energy that it takes to do this experiment is way more, because we have to cool down our experiment. It happens at a couple of Kelvin. So that of course takes, also the measurement, the electronics themselves, they take a lot of energy. So in that sense, you have to be a little bit careful where you draw your dashed line and say this is the amount of energy that's being used by the system and all the stuff around it. But it is the theoretical limit that at least we can measure now. Yeah.
Do you know how what the difference between a quantum computer and a traditional computer? Like a traditional computer uses binary to do everything. What does do you know what quantum computer uses?
Yeah. So well, I won't be able to explain it in 5 minutes. But so the basic principle of a quantum computer is that, exactly as you say, in a classical computer, it's either 1 or a 0. It will be a spin up or a spin down. Now from quantum mechanics that things can be in a superposition of states, right? It can be spin up, it can be spin down, but it can also be spin up plus spin down, or spin up minus spin down, or spin up plus e to the power phi times spin down. and e to the power I phi, sorry, with a imaginary. So you have essentially a phase between spin up and spin down. So you can think of it as a phase, right? And this is in this phase, this complex number. That's where you encode your information. So the power of quantum computing in that sense comes from the fact that you're not doing your computation with a binary number, but you're doing it with a complex number, with a complex phase. And that is for certain kinds of problems, not for everything. Like for okay, let's just leave it like that. So for certain problems, that can be very efficient if you can make use of that phase rather than just having one or zero.
So like it could be like a 1 and a 0 at the same time.
Yeah, that's hardcore quantum computing, quantum algorithm people will kill you if you say that, because that's not really what superposition is. It's not really two things at the same. Yeah, it's more, but sort of the simple version of it is yes, it can be two. It's in two states at the same time, and there's a certain phase relation between those two states.
Yeah. I think one of the reasons it's so hard to understand is because this is completely like quantum mechanics is on the chip. There's no really like conceptualizing.
Yeah. So one way in which people sort of think about these superpositions to visualize them in some way is on what's known as a Bloch sphere. So if you think of a 1 or spin up as the north pole of a sphere, and the 0 or the spin down as the south pole of the sphere, then any superposition, you can think of it as some point on that sphere. So for instance, spin up plus spin down would be sitting somewhere on the equator, would be sitting here, and then spin up minus spin down would also be on the equator, but on the other side. And then the complex ones they're sort of here and there, and then any operation that you do is sort of a rotation on that sphere. So you can sort of rotate it, and those are essentially the quantum operation. So with a classical computer, the only thing, you're always on the north pole or the south pole, and the only operation you can do is either stay on the north pole or go to the south pole. That's it. Whereas now you have all this extra freedom to move over that entire sphere.
How's the work that you've done recently contributed to the quantum computing side of things?
So I think the stuff that I showed you earlier, the silicon, that was really geared towards making a silicon quantum computer. I think the things that we do now with the molecules, that is more sort of basic understanding, sort of more fundamental. So all the sort of thermodynamic questions, that's really trying to understand how thermodynamics works on the nanoscale. Now, of course, if you have a quantum system, especially if you have a qubit that can be in a superposition and you can manipulate that superposition, there's actually very interesting questions about whether this classical thermodynamics picture that we have, whether that still holds. Because like the second law of thermodynamics is holy, right? Thou shall not break the second law of thermodynamics. But is that still true for a quantum system if you bring it into a superposition? So those are the sort of fundamental questions that you can ask, and we're sort of just starting to be able to ask those questions, because it is only now becoming possible to measure classical thermodynamic quantities such as entropy of these nanoscale quantum systems.
We had a.
Can you tell me the recent research is going on quantum tunneling?
Sorry?
Quantum tunneling, what is happening with quantum tunneling recently?
Quantum tunneling. So quantum tunneling in a way is so everything that I've showed you here, it all relies on quantum tunneling. Quantum tunneling, in a way, is a fairly so people talk about quantum 0.1 and quantum quantum 1.0 and quantum 2.0. Quantum tunneling is kind of quantum 1.0. It's sort of stuff we know that it happens. We actually make use of it. So there are electronic devices that, you know, like lasers and things like that, that actually rely, or some transistors, also some diodes rely on quantum tunneling. That's something that and that is really technology that makes use of superposition and entanglement. So superposition is the thing that we've just talked about, you know, being able to be not just, you know, spin up or spin down, but anything in between. Entanglement is the sort of two-particle version of that. And if you can use that as a resource for either computing or for sensing, that is really what all those quantum technology hype is all about at this point.
We had a lecture. We had a lecture quite recently with Hobson, where he sort of explored looking at using older technologies in very modern, I guess, science. He was using Bakelite in Atlas, for example. And I guess you kind of used what some people see as quite old science. You know, at the end of the day, thermodynamics was finished in the 1890s. But you're applying it to a very modern quantum mechanics, which, to be fair, a lot of that has also been completed in the 60s. So, would you agree that it was our class of thermodynamics that inspired this work?
Absolutely, absolutely. Yeah, I think if I hadn't started teaching thermodynamics 3 years ago, none of this would have happened. Yeah, absolutely.
So are there any other questions? Have we done anything super yet with quantum computers? Because I know they've only kind of come out recently, like when we did invent classical computers.
Yeah. Maybe. So people talk about this.
Chinese did some experiment related to quantum.
Yeah, well, so people talk about this thing called, for quantum computers, they talk about quantum supremacy, which I find a bit of a nasty word, but where quantum computers are better than classical computers. And there are beginning to be problems now where a quantum computer outperforms a classical, but they're very selected problems, and some people are very critical about it, and they say, actually, you know, the only problem that these quantum computers can solve is the problem that was designed for them. It's not a useful problem. It's just. But I think that's sort of on the edge now, where they start to become, for very specific problems, they start to become more powerful. It's still, I think, when I started my PhD in what was it, 13 years ago or so, then there was a huge gap between what people that were working on quantum algorithms, what they needed in terms of how many quantum bits, how many qubits, and how many qubits we actually had. Like, you know, there was 1 qubit, 2 maybe, and they needed 1 million. And I think in recent years you've seen that these things have come closer together. So the number of qubits is still, it sort of counts in the hundreds now, I guess close to 1,000 perhaps. And the number of qubits that the people doing algorithms that they need has come down a lot. So they're sort of about to meet. And I think once that happens, you can actually start doing useful stuff with it. So I think it's about to happen.
Would you say then that we've kind of invented the technology for problems we don't yet have?
That has been a problem, I think, at least, especially in the beginning. If you don't have the computer, it's very difficult to come up with an algorithm that a computer could solve. but that's changing now, I think. So there's actually ways of simulating what a quantum computer would do. So you could sort of simulate what your algorithm would do. So I think it is getting there. Yeah, it used to be just like fusion, like nuclear fusion, which is always 5 years or 10 years ahead. And that used to be the joke with quantum computing as well. Oh yeah, we're just 5 years away from it, and it just keeps shifting. But I think that's no longer the case. I think it's really getting there. It's also like big companies like Microsoft and Google. They're investing massively into it, and that really makes a big difference, obviously.
Well, I'll say thank you very much for the talk. For those of us who are in maybe third or fourth year, that was a very interesting look back on sort of the stuff we've learned in quantum and thermo. And for those of you that are in first year now, that's quite an exciting look forward at what's to come. There was a lot there that we recognise, certainly in Luke, from our previous course that you've got to look forward to. So thank you very much, Dr. Jan.
Thank you.
Yeah. Thank you very much.
Thanks. Switch off the recording, eh?
Yeah, there we go. You know what I was talking about.